Okay, again, as there seem to be more questions, I think you're happy find your during the breaks. This gives me the chance to introduce our final speaker today is Rhun. I hope it was right, sorry. He's from Thales Research and Technology. And he will talk about safe, secure, and reliable computing with a NOEL processor. Please.
Thank you for the introduction. Just a quick introduction for Thales Research and Technology. It's the corporate research center for Thales Group, and where we do applied research and technology transfer to Thales business units. And 2 labs are involved in RISC-V activities, the High Performance Embedded Systems Lab and the Critical Embedded Systems Labs, of which I'm part of. So we have quite a few contributions to the RISC-V ecosystem. One of my colleagues is chair of the Functional Safety SIG at RISC-V International. We are also involved in the Open Hardware Group, with a co-chair in Technical Work Group, a leader of the CBA6 project, and we were also involved in the IUMMU specification. But you will have more detail on that with the keynote from my colleague Thierry Colette on Thursday morning, so make sure not to miss this one. In addition to all of that, we are also doing specific research activities for critical systems to improve safety and security properties. And especially we did, the topic I will talk about was made in collaboration with Thales Alenia Space for specification and evaluation of space-grade system on chip. So, as some of you may not be aware of the challenges of safety critical systems, let's have a quick look at this. Either about aircraft or trains or, in this case, space systems, we have very strict requirements for dependability and standards to respect about this. So strong robustness requirements because systems are working in harsh environments. Lots of fault tolerance properties needed when we need the system to keep operational even in case of failures. And deterministic real-time behavior because this is especially difficult in multi-core systems. You can have timing interference when several cores try to concurrently access shared hardware resources. And these resources can be I/O peripherals, it can be shared memory, and also all the paths linking them. So it can go quite deep into the architecture. But at the same time, we have an ever-increasing need for performance. Algorithm gets more and more complex, datasets gets huge, and we have multi-mode applications, multiple applications running on the same system, and we need them not to interact with each other. We don't want an application to miss its deadline because the other ones are taking resources. So we don't really care about the average case performance. We want a guarantee of the worst case performance. And on top of that, we have lots of new requirements about increased connectivity amongst embedded systems and towards the cloud, for example, which brings also a lot of cybersecurity concerns. And ideally, we want all of that free from export control restrictions. The thing is, safety critical systems is a collection of small markets. We don't have the critical mass to do a big chip design and deploy lots of billions of chips on the market. And so it was not really cost effective to design custom hardware, except in this case for space, because radiation tolerance is so hard. You really need to invest in that. But the new space wants much cheaper solutions to deploy large constellations. And using multi-core quotes gets increasingly costly because you have to reverse engineer lots of details in the arbiters and everything that is not documented in order to make sure that you can manage the interference you get on shared resources. On the other hand, open source has many great advantages. as it's open, we can look into it, we can observe what is happening in the design, and we have ability to document missing bits for certification, for example. We can even perform cybersecurity audit. It's lots of work, but at least it's possible to do it. Open source is also very good to respect standards and for interoperability. And the larger the user base, the better the test coverage is. Open source hardware is not something completely new. We have been, for example, having the Leon Spark as a European success story for space. But again, it's really a niche market. And seeing the great momentum with RISC-V ecosystem, as we can see with the attendance here today. So this is a great opportunity to introduce safety constraints in the community and make sure that IPs can take into account those challenges and can be used in those domains as well. So in the De-RISC project, what approach did we take? So De-RISC, it means dependable real-time infrastructure for safety-critical computer. It was a fast-track to innovation project running for 3 years until last September, and very focused project with only 4 partners. And the goal was to develop a fuel computing platform for space, including a fault-tolerant multi-core architecture on FPGA proposed by Frank Gessler from Sweden, with a extra 2MNG space-grade hypervisor from Ventis in Spain. Also advanced monitoring techniques from BSC, also here in Barcelona, and validation with space application performed by Thales. So the complete platform is fully made in Europe, and I will talk a bit later about the follow-up ESA-supported program for an ASIC. So the platform is based on the NOEL-V core from Frontgrade. It's an RV64 GCH core, quite powerful because it has a dual issue pipeline, and it conforms with the OSA embedded platform specification. I won't go into all the options and extension it implements because it's quite long, but yeah, it's really a full-featured core, and it's available under GPL and commercial licenses. The De-RISC platform instantiates 4 of those in a system on chip with dedicated I/O for space, extra 2MNG hypervisor, and the SafeSU module for monitoring of interference. It was implemented on Xilinx FPGA, and there are demo bit streams available for Xilinx and microchip evaluation boards, as well as this board developed during the project. One of the key property we want to add in the ecosystem is the isolation of application. We want several applications running on the same computer not to interfere with each other. One way to do that is to support hypervisor. So a result of the project is the implementation of the H extension as soon as this was ratified, maybe even earlier, into the NOEL-V core, and its support by Extratom hypervisor. And this has been validated with space payload framework from the French Space Agency called LVCU-GEN that we ported on top of the platform. Also, we use physical memory protection and IOMMU to really isolate the different applications and make sure that each one only access to what it needs to. And to ensure that we don't have interference on the interconnect, we developed a low interference interconnect based on the address stripe multibus. So this looks like this, with 4 buses, 4 AHB buses, and all cores are connected to all of these stripes, as we call them. But we can choose which one we use depending on the address. So by default, it maps to the cache lines. But using higher address bits, we can have completely segregated data path going through the partition L2 cache, down to the multi-port memory controller. So we can have completely interference-free islands, as you can call it. It's like having your own lane on the highway, so you don't get traffic jams in this way. There is also a time-slotted mode still under development. It's a more traditional way of doing it, but it has, of course, a performance impact. Another important thing is the reliability. Especially in space, we have lots of cosmic rays that can flip bits in the memory. So the core implements ECC on each and every memory, including internal caches and register file. Of course, it also has it for external memory. So it's a quite powerful ECC encoding. And there is also a hardware scrubber to exert this correcting mechanism to avoid error buildup. Radiation testing has been performed during the project, and the results have been published in the RADEX conference. And we are now implementing the control flow integrity. The standard is still ongoing, ratification. And so it's about implementing software shadow stack and landing pads. So what are we working on right now? It's within an ECF-funded project. We are contributing to an octa-core processor in ASIC implementation, having 5 NOEL-V cores or 5 Leon-5 cores. And it gets quite high performance. It has also the striped interconnect at its core. And we have, I won't go into each and every box, but we have quite a lot of peripherals and interfaces, and it's a very complete platform. We'd expect quite a high performance compared to other chips in the domain with 1 GHz processor frequency. And the implementation target is on STM 28 nanometer FDSOI. So again, a technology providing a very low power and high resilience to radiation. So in conclusion, RISC-V is a great opportunity for critical systems. The openness will allow us to regain control on fine-grained hardware features that we cannot access easily with components off the shelf. It allows us to implement solutions for safety and reliability, and to tailor jointly the hardware and software to take advantage of those mechanisms. And it's also a great opportunity to team up across application domains to inject the right amount of properties and features for safety, for different level of safety, depending on your final application. The De-RISC solution is an open, safety, and determinism-oriented multi-core system on chip with a complete and certifiable software stack. It has been validated using space-grade software, and there is an ASIC coming soon. There is already the first NOEL-V has been sent to orbit almost a year ago, and it's orbiting fine, and there are for sure many more to come. Thank you very much. If you have questions.